We're talking about size, okay? So more size or mass equals more heat energy, okay? So I am plushier than Ashanti, okay? Everybody can see that. Even though I've lost a little weight, I'm still plushier than Ashanti. So, in terms of heat, who is going to have more heat? You. Me. She's a little skinny thing. She's going to freeze death in the winter. I got a little insulation on my bones here. I am not going to freeze to death in the winter. Okay? Now, when we go back to temperature, does temperature have anything to do with size? No. No. Her body temperature and my body temperature have nothing to do with size. Our body temperatures are both supposed to be 98.6 because if we're both sitting in the room not moving, we're both going to be 98.6. However, this is about size. I have more mass, more size than Ashanti. I'm going to have more heat. She has fewer molecules on her frame. We can all see she's smaller than I am. She's going to have less heat. Okay? That's just the nature of our body sizes. You with me? Okay. So, this is the key. Heat is about size. Temperature is about motion. Okay? So, when you go outside and run around, what goes up? Your temperature goes up. Not your heat. Your heat is about your size. Your size is not going up when you go outside and run around like a fool. Okay? So those of you who have third lunch or in the courtyard and watch William, Logan, and Jacob's antics in the courtyard, their temperature is going up. Their heat is not. Does that make sense? Everybody with me on that? Okay.
He said it's going down.
Say what?
He said something's going down.
What's going down?
Huh? I heard him say something's going down. I don't know.
I don't know either.
I'm confused.
All right. Is everybody caught up with me?
Yeah.
Okay. So, if we look at this picture.
Oh, man.
All right. Which one would have more heat?
95.
Why would the 95 have more heat?
More thing.
All right. It's got more water. When you look at it, can everybody agree that has more liquid in it? Okay. That's why it has more heat. Everybody good with that? All right. Got more. Whoops. All right. Which way would the heat transfer? If I put the two together, which way would the heat transfer?
From left to right.
Okay. Since this one has more heat, heat moves from warm towards the cold. All right. All right. Let's say we put a hot nail in a frozen glacier. All right. Which has more heat?
The hot nail.
All right.
Glacier.
We got a hot nail. We got a frozen glacier. I want you to think about it.
Oh,
Okay. What do we say has more heat? I heard it up here on the front.
Because it's more.
Heat
It's more.
is about size.
Yeah.
The bigger.
Okay? So, which one's bigger? The glacier. And the why is because it's bigger. Okay? It doesn't matter that the nail is hot. It could be glowing red like an ember. But when you think about a glacier is mammoth. What's the size of a nail? Yeah, like maybe our finger. Okay? Maybe we got a bigger nail and it's 2 fingers in length. But regardless, it's still, an appendage finger size. It's not gigantic. When we think about a glacier, glaciers are huge. They could be the size of the school building. And it's still frozen, but still. When you add all that together, who's bigger?
Glacier.
The glacier. When you add all those molecules together, it's going to be bigger in size. So it's going to have more heat. Now, from there. Oh, I'll leave that there. Get out of there. All right. Do all states of matter have a temperature?
Yes.
Do all states of matter have a temperature?
Yes.
Yes. Okay? Yes. Do they all have heat?
Yes.
Yes. They both have a temperature and they both have heat. All right? Now, the question is why? Why do they both have a temperature and a heat? Since I heard some people out there yelling no.
Because they all molecular matter moves and all matter has weight.
Okay. All matter has motion and
Mass.
it has mass. I like that word better. Okay. All matter has motion and it has mass. Okay. Every single piece of matter has motion and it has mass. Now, some of you are thinking, oh, it doesn't. Does the desk you're sitting in have motion? On a molecular level, it does. The molecules that make up that desk, that make up the pencil that Alexis is writing with, that make up the paper you're writing on, those molecules move. Okay? Every single object in this room has motion. The wood cart back there, the computer, the wood tables that Damien was propped on. At least he took his foot off the leg. All right? All of those things have motion. When does motion stop?
Never.
It does.
It does.
Hmm? Most people don't know when, but it does.
It freezes.
That's usually the answer I get. Gotta be colder than freezing though.
Like
Below zero.
You might have known or know it if you took Mr. Al's class. Sometimes he talks about it
atomic
in Principles of Tech.
atomic froze.
No. So I got a name. All motion stops at a point called absolute zero.
Oh, I heard that.
Have y'all heard of that before?
Yeah.
All right. Absolute zero is defined as 0 Kelvin.
What? Kelvin, what's up, Kelvin?
Kelvin is a temperature scale that we don't use in physical science. All right. 0 Kelvin is equal to negative 273 degrees Celsius. Now, for those of you who are familiar with the Celsius scale, you have an idea of what that means. But for us, that's negative 457 degrees Fahrenheit. Some of y'all probably came in this morning when it was around 38 degrees Fahrenheit and were like, dang, it's cold outside. Let me in the building. All right? Now, 38 degrees Fahrenheit is above zero. We're not even at freezing yet. And we need to get almost 500 degrees colder to get to absolute zero. Life is not sustainable at 500 degrees colder than this morning. Okay? Now, if you've seen shows like Bill Nye Science Guy and other things where they, I know, I always get people who say that, who take like tennis balls, bananas, put objects in like liquid nitrogen, and then pull it out and shatter things, or use like the banana as a hammer, and demonstrate what happens with liquid nitrogen and liquid oxygen. Those things are not at absolute zero yet, okay? It's incredibly cold to get to absolute zero, to get those molecules to stop moving. When you're dead, laying in the casket, are we at absolute zero?
No.
No.
No. Are the particles in your dead body still moving?
Yes.
Now, it's an incredibly slow rate. But if the particles weren't moving to some degree, could your body decay over time?
No.
No. Okay? Remember, when you're put in that casket, even though you've been embalmed, over a period of 20 years, are you going to, when they dig you back up, are you going to look like you did when you were buried?
Bones.
No. eventually the hair's gonna be gone, the skin's gonna be gone, fingernails are gonna be gone. You're gonna be some bones laying in a casket. Okay, you're not gonna look the same way. So all of that has to decay and go away. If your molecules were not moving anymore, would that process occur? No. Okay? So those molecules are moving at an incredibly slow rate, but they are moving for that process to occur. Okay? At absolute zero, all motion is stopped. Okay? So motion is happening even inside of here. It's just incredibly slow. I mean, the table's not going to vibrate out of the room, but the particles inside are moving at a slow rate. Now, in a liquid or a gas, they're moving much faster. Okay? Now, last thing before we do our activity. All right? Why do some objects stay hot longer than others? Or why do some objects heat faster than others?
More mass or more motion.
Okay, it's not a bad guess.
Something that.
That one wrong though.
Some do. All right. There's a word we're going to talk about. Okay? Some materials have a different specific heat. Okay? Now, we're going to use two examples I know you can relate to, and I'm going to use a third one. Now, let you write it down before I talk about it, because we're going to use water and aluminum because those are easy examples everybody can relate to. Even I can tell from here, some of y'all, there's stopwatches. Somebody set the alarm. Of the ones that are still working that haven't been broken apart. Those are the worst stopwatches I've ever bought. You push the button, it cracks the side open, and the buttons go in the middle. And I know that because I broke one myself.
Have you been waiting on?
He doesn't usually.
I don't worry.
He just fails.
I just paid attention.
Hey, it's
That's
better
why you
than
don't
writing.
make me grade on the quizzes.
Your brain works better writing.
It really does. You remember from me?
I learned it in first grade.
Good job, boys.
We're learning about memory and stuff.
Now, the numbers I get ready to write down, you don't have to memorize. I'm just using them for an example.
I need to get my.
So how much is foreign, dude? She's like a lot to remember.
Took it already?
Like she messes with your brain. Like she has these goggles where you have to look up to look down and look down to look up.
I will.
And try to. She made us like try to walk and shake each other's hands. You know how
Oh, it
funny
was
that was.
loves class.
You know how funny that was.
I will.
Listen to what. And then the other pair of glasses, you gotta look like it threw off like 20 degrees. Like you gotta look 20 degrees this way, look 20 degrees that way. It's crazy.
All right. Is everybody caught up with me, or do I need to wait?
You caught it.
All right.
I will.
You can see Alexis and Janai are still writing.
Was it the door?
Tell me when you got it, Janai. I don't think I have the numbers there. Nope.
There's some babies also.
Got it? All right. Yep, I put them there. All right. I actually put them up here. Now, you don't have to memorize these numbers. I'm only putting these numbers here to illustrate what we're talking about, okay? So, here are some specific heats of some things that we have used. The zinc we used way back at the beginning of the year. Remember those little discs we used in that very first lab we did?
Yeah.
All right, it's just a metal that we use sometimes. But water, copper, and aluminum, I know y'all are familiar with. All right, water we use all the time. Copper we use in wiring, and we've used, some of us have maybe pans that have copper bottoms. Aluminum foil, how many of y'all use, I'm lazy. I don't like to wash foil or pans a lot. Particularly, let's say I'm laying something out on a pan and I don't really want to scrub the pan at night, so I cover it in full. Or I'm heating bread and I don't want to have to, yep. And so I just wrap the bread and throw it in the oven, and then I need to pull it back out. Or I think I've told you this before, my kids hate grill marks on chicken, and so I line the grill. And that's strange. I know, strange kids. So I throw foil down on the grill, and then I put stuff on the grill. So I use foil a lot at my house. So when I use it, how long does it take the foil to cool? Take a long time, or does it cool quick? It does. Cools very quickly. All right. So aluminum cools very quickly. Okay. And if you don't know this, copper does too. All right. What about water?
Nope.
Nope. What happens then?
It takes forever.
Takes forever to cool. Okay. All right, so it cools very slowly. All right, what if we try to heat it up? Does it heat quickly or heat slowly? It heats slowly. All right. If you're trying to make, let's say, spaghetti noodles or rice, and you stand in the kitchen watching the water, it takes forever, doesn't it? Okay. All right, so it heats slowly too, and it cools quickly, for those of you who've not pulled full off. Okay? As soon as you take it away from the heat, it's cool. Oh, I wrote slowly twice? Yeah, I did. I meant to say heats quickly. Get rid of that. Heats just as quickly. All right? Put it in the oven. Gets hot almost instantly. Now, what does that tell us about a material?
The bigger the bigger the number, the
bigger the number.
Yeah.
That's right. It's exactly what it tells us. Let's see, do I have space to write it there? No, I don't. All right, got a space right there. Yes. All right, so what do these numbers tell us? Let's just say this. Large, specific, heats, heat, and cool how? What do these large specific heats tell us? They heat and cool how? What does this large specific heat tell us? They heat and cool how? Y'all are killing me.
Oh wait, what?
This large specific heat. It heats and cools how?
Slowly.
That's right. All right. These small specific heats. Okay. So this small specific heat.
Heat and cool very quickly.
Yep. It heats and cools quickly. Questions? Any questions? Because you got to be able to use it shortly. Sure. You're going to have to. You've got to give them to me at the end of class, so you're not working on them at home. And it is a grade.
What did they do?
I'll be, well, I don't know, a couple of you might get it finished today. Who's you work quickly, but most of you will need time on Monday.
Yeah.
No, it cannot be for homework. William, did you hear me say that? It cannot be for homework. Y'all have to give it to me for my safekeeping for the weekend. Did everybody hear me say that?
Yep.
You cannot keep it. You have to give it to me for the weekend.
You cannot work on that.
You cannot work on them at home.
I won't work on them at home.
Right.
Forget.
All right. John's had a rough day apparently.
Where's my dollar game?
All right. Now, let's talk about what you're going to do real quick so that everybody knows what they're doing and I don't have to answer the same questions 500 times. Now, at the bottom, at number 7, can everybody make out the temperatures? Sometimes these get cut off and they're hard for people to read. In A, it says 70, in B, 50, and C, 25, and then D, it looks like the 50 got a little chopped off. Can everybody read that? Okay, because you're going to need that on the back side. All right, so you're going to, on the back, draw a graph. Whoops, let me get a page I can write on. All right, so you have a graph on the back side. Everybody see it? Big graph. All right, and it tells you in the directions to plot a graph on the horizontal axis. You're labeling what?
Are you good?
You okay over there?
Yeah, I just dozed off and I was sliding like y'all just looking at me.
I know, we're just going to leave you.
You're all doing Tom.
Okay? So is everybody with Logan? On number 1, it says plot time on the horizontal axis. We're putting time down here. Okay? On your vertical axis, you're plotting what? Temperature. Now, you're plotting 3 lines on this graph. Okay? So you have to show me a key some kind of way. Some people like to color on this to draw me the key. Some people prefer to draw A, B, and C on here to show me the key. I don't care how you do it, as long as you tell me which line is which color, so I know which line is A, B, and C on the graph. It doesn't matter to me how you do it, okay? But I need to know which line is A, B, and C. Some people just write A, B, and C on the line, so I know, so I don't care. You choose. Now, you're going to plot, and the easiest way for me to explain this is to say, cover up, and these are not going to be exactly straight lines, so you don't need a ruler. Cover up B and C, so you're only looking at time and A, okay? Now, you've got to create an interval for time. You got to go from 0 to 120, right? What would be a good interval to label along your x-axis if you got to go from 0 to 120? Okay. Number from 0 to 120, counting by tens then. Do it now. Everybody should be numbering from 0 to 120, counting by tens right now. 0, 10, 20, 30, on your graph. Are you okay over there? You only need to go to 120 because your time's not going to exceed 120.
I don't know what I did with my pencil.
Was it yours or did you borrow it?
That was mine.
That's at least one thing. That's good. I don't know if I have any over there or not. Now, for your y-axis, you're going from 100 down to 50, but all of the graphs start at 100, right? So, you're going to have to estimate a lot of these. What would be a good interval to count by?
What, 100? 500?
I would say 5. So, start at 0, 5, 10, 15, 20, 25, so forth and so on. Get up to 100. And then stop at 100. Does anyone have a pencil that long, Jacob? Jacob. David's handing you a pencil. Give it back to him at the end of class. You can do it yourself. Okay, everybody good with the number?
You said it's 100, right?
No, don't yet, because you got to do 3 colors. I'm gonna let you get them get color pencils.
On this one.
You're going from 0 to 120 on the X and 0 to 100 on the Y. Yes. All right. Now, you have to use 3 colors. Is everybody okay with the numbering before I talk about the other instructions? All right. So, the easiest way to do this, you and these Friday notes. Don't you love them? Isn't that right, John? I think she figured out I only turned in one of these this year.
Can you get out?
I have to give everybody one. I will not feel slighted if I'm not on the list. All right. So, if y'all cover up B and C for just a second, y'all are going to graph A, okay? Time and insulator A in one color. You pick any color you want, okay? Back there on the table with William are colored pencils, okay? Insulator A. Then, cover up A and C, okay? I'm just going to cover up C and A. So, you're going to graph time and B. Pick any color you like. And then you're going to cover up A and B and do time and C any color you like. So you need 3 colors. You're going to draw 3 separate lines. They're not going to be straight. Okay? Once you have the 3 graphs, then you're going to answer the questions using your graphs. You got me? Go forth and prosper. Groups of 2. Not groups of 4. Not groups of 6. 2.
No, I said 2.
Well, you know, I have to be clear for some of us.
As well.
Yes.
Things to that.
We're less than 15 minutes from the bell.
Sitting there dying. I was dying.
No, you didn't.
Hurry up.
You didn't even let me
What's the
go.
bonus?
On the back side of that.
I was waiting for you.
Somebody get it.
Leave you with 1.
Hey, Daniel,
Any 3 colors you want.
you already got 3 colors? Yeah.
Oh,
Huh? Yeah.
You don't even have to use the same color as a partner.
You missed.
You can use a different color.
Come on.